I'll start the recording started. All right, yeah. So good morning. It's now 9 o'clock, so I'm gonna go ahead and get started. This is day 3 of the physics camp, the last day. Um, up till now we've talked about vectors, we've talked about forces, and now today, as you can see from the title, we're going to be talking about equations of motion. All right. So let's see. Let's get right in. Why does it look like that? Okay. Excuse this little tint over it, but you can still see it. So, equations of motion, right? Yesterday we talked about forces, and forces tell us why an object moves. You apply a force to an object, it causes it to move. So, the force would be the reason for the movement, right? So today, we're talking about the equations of motion, or in other words, kinematics. Kinematics tells us how an object moves. So, how an object will move through space. Okay. How an object moves. All right. Cool. So basically, I kind of just want to go over the basic words we use to describe how an object moves. And those words are basically like words like displacement, position, velocity, acceleration, and time. Um, then I'm going to get into a little bit of the graphical representation of, velocity, acceleration, and time. Um, then I'm going to get into some examples with constant acceleration, and then I'm going to end it up with projectile motion. And I don't know why my slides keep slipping from one slide to the next. So first, so when we talk about how an object moves, the first thing you need to describe it is, you use its position that it's in to describe where it's at, right? And so first I want to talk about displacement and distance. So distance is basically the total length an object travels during motion. And distance we think of as a scaling. Where a scalar is an object that just has, a magnitude. It doesn't have like a direction associated with it. Whereas displacement is going to be your final position minus the initial position, which is, displacement is a vector. And for everybody that's kind of just not getting in, we're going over equations of motion. So let me kind of give a quick solid example to show the difference between distance and displacement. So let's say we have a person walking here, and over here is 0, way over here, let's say it's 10 meters. All right. And let's say he walks from there all the way over here to the 10 meters. And then he walks back walks back halfway, let's say it's like right here. It's at 5 meters. So first he's here, he walks all the way over here. I don't know, let's say to give this guy a high five or something. And then he walks back this way. Then he's here. So just to kind of recap this question again, this person, starts at I guess called the origin or at 0 or at home, or anything. Just starts here at 0. He walks all the way over here 10 meters away to give this guy a high five at 0.2. And then he walks back 5 meters here at 0.3, and he's just stopping, standing there looking at a bird or something. So now I can ask you the question, what's the distance this guy traveled and what is his displacement? So distance, this distance, I'm going to use the letter D for that. This distance is the total length he traveled, right? So that's pretty straightforward. Well, he went this way 10. Yeah, exactly. So distance is 10, displacement is 5. Somebody already gets it. Nice. So yeah, his distance is going to be the 10 plus the 5, right? So it's 15 meters. All right, and his displacement, which is going to be his final position minus his initial position. Well, initially he's at 0, and his final position is here at 5. So I'm going to use displacement as a triangle. This is a delta. This is a delta. Whenever you see a delta symbol, it's not just a triangle. It's a Greek letter. It's supposed to be like a little bit folded on this side here like that. It basically means a change of. Whenever you see delta with another symbol, it basically means the final minus the initial. So it's always going to be the final minus the initial. So the final position was 5, the initial position is 0. So the displacement is 5 meters. Cool. So cool, got that out the way now. So now we kind of know the difference between distance and displacement. Displacement is just the final position minus the initial position. Okay, cool, which is different from the distance, which is going to be your total length traveled in the motion. All right, that's not bad. So the next thing we kind of need to describe is velocity and speed. And the main difference between velocity and speed is velocity is a vector and speed is a scalar, but they're not the same way displacement and distance is not the same. So a velocity is a vector, so we represent it with the v with the little line on the top, and the vectors have x and y components in 2D, but let me actually throw in another one, y, z. So I know up until this point when we talked about vectors, I wrote them out as just, an x and a y component. So you can kind of immediately imagine, well, that's just 2 dimensions, right? It can easily step up to 3 dimensions if you add a z component. Not that we'll be doing any examples like that, but just to kind of show that, this can easily jump up to 3 dimensions if you use the x, y, and the z plane. But yeah, so velocity is a vector, and velocity is going to be represented as, it's going to be given as the displacement, so your delta x divided by change in time. All right, similarly, your velocity is going to be your displacement in the y direction divided by the change in time, so on and so on. Similarly for the z direction. Okay, so still nothing too new yet. So velocity is basically the displacement divided by the time. Makes sense, especially if you think about the units for velocity being meters per second. So we've got meters over some time. So this is delta x in meters divided by the change in time. Okay, so now speed, which is a scalar, is given, the equation for that, which I'll use the s, is the distance divided by the time. All right. So speed, which is a scalar, is going to be your distance divided by the time. So not the displacement, but the overall distance divided by the time. All right. Okay. So now let me do a quick example of this with some numbers. So let's use the example I used a moment ago of this guy walking 10 meters. And notice this is one dimension, right? It's all on one straight line, so we can call this the x-axis. That's in one dimension. Let's say it takes him, I don't know, let's say it takes him about 20 seconds, right, to walk 10 meters. So at the time it takes, so real quick, if you're just coming in, try to refrain from going through the slides here, because everybody can kind of see you switching through them and erases what I write. But if you are just kind of rolling in, you just want to see what we're talking about, write in red for I'll rewrite it. So just to kind of quickly recap, because there's still a few people rolling in, we're talking about kinematics, where kinematics is basically how an object moves. And a moment ago we talked about displacement and distance, and now we're talking about velocity and speed. And I was given the example. Oh, you asked what I wrote in red, right? What I wrote in red was speed. S is given by the distance divided by the time. Whereas the velocity, yeah, I got you. Where velocity is the displacement over time. I'll write it this way, displacement. Okay. So going back to this example I kind of gave a moment ago, we got this guy here. He walks 10 meters. So let's say it takes him 20 seconds. It takes him 20 seconds to walk 10 meters. So you can ask, well, what is his velocity? And the velocity is in the x direction, right? So velocity in the x direction is going to be the displacement in the x direction divided by the change in time. And so his displacement for this first part is just 10 meters. Just looking at the part where it goes from 0 to 10. And so displacement is going to be 10, and the time is going to be 20. And so his velocity is going to be 0.5 meters per second. Right? Alright, cool. That's pretty straightforward. And notice if I were to ask you what was his speed, it would be the same thing in this case. Because the distance traveled is 10 times 20. So the speed is the same. Okay, cool. So now let me have him go through his whole motion of walking over here and then walking back into the center. So it starts over here at the right at 0, walks all the way over here 10 meters away, and then goes back to the center here at 5. Numbers on the top representing the order that he went. So it started here, went over here, and then went into the middle. So now I ask you, well, what was the velocity through this path? Switch color. So velocity in the x direction given by the displacement, right? Displacement on the top. Yeah. Just rewrite it. Yeah, so again, you could just coming in and try not to skip through the slides. So, so yeah, we're talking about velocity and yeah. So the velocity is displacement, right? So delta x over delta t. It's not still 20 seconds. Let's make it 25 seconds now because it's going to be a little extra time. Let's make it 25 seconds, right? Because he has to walk, all over here 10 meters and then back into the center. Back into the center here. All right. So his displacement, if he walks back to the center of 5, you already know his displacement is going to be 5. But I'm going to write it out here. So it's final position, which is 5, minus his initial position, divided by 25. So what's that give us? That's a fourth, so 0.25. That's meters per second. And so if I were to ask you what was his speed, Again, speed is given by the distance over the time. Okay, well, the distance is 15, right? Yeah, 15. So we have 15 divided by 25. So his speed is, I don't know that off the top of my head, 0.6 meters per second. Okay, so yeah, so far, all we've talked about then is just displacement, and velocity, and how displacement has its kind of scalar counterpart, which is called distance, and how velocity has its scalar counterpart, which is called speed. Okay. And so now let's look at some how this is represented in graphs. Before I did give this equation for velocity. It's given by this here. But this is actually the average velocity. This is average velocity. And I think the best way to kind of show the difference, well, so there's something called average velocity and there's instantaneous velocity, right? There's velocity over an average, and there's then velocity have at a certain instant. And so I think using a graph would be the best way to kind of show the difference between those two. So here we're going to look at a position versus time graph. So position, hold on, what's that? So position versus time graph. So we can call this is our okay. So I think I'm just going to have to share my screen so I can kind of control what's going on a little better. Let's see. So hopefully this works out. Yesterday I was having a little problems with sharing my screen. So you guys can see my screen, right? And you can still hear me? Slideshow. Let them start. Okay. Just gonna assume you can still hear me. So yeah. equations of motion, kinematics, right? We talked about displacement and distance, velocity and speed, and now we're going to look at how that looks on a graph. So if we have this position versus time graph, so this our y-axis is going to be the position, so let's call that x. Then this x-axis is going to be the time. And similarly, this is going to be a velocity, and this is going to be time. Right, so let me just draw a quick graph on here, and then I'll kind of explain what's happening. Okay, so looking at this position versus time graph here, you see that, there's some slopes, there's some flat parts, there's slopes that goes down, there's some slopes that go up. So let me kind of explain what's going on in each part of the graph here. So, and I think it kind of takes some getting used to as far as looking at these kind of graphs, because the x-axis represents time, which, you kind of have to think about that a certain way. So you can kind of imagine for this first part here, for this part of the graph, you see, well, as time goes on, this person is walking from, let me put numbers on there too. So this is 10 meters. Let's say this is 20 seconds. And so right there, this would be like a person walking or moving. I guess this would be like a walk, right? Because it takes me 20 seconds to walk upward to that 10 meters. Okay, that makes sense. So here, the flat part of the graph, I guess I'll ask you, what do you kind of think this person is doing? So if you've thought about it already, if you've already kind of, got an idea, you can kind of imagine that this flat part of the graph, a person just standing still. So he's just standing still, right? Because notice as time goes on, which shows that it's flat, he still remains in that same position of 10 meters. So this flat part of the graph for a position versus time graph just represents a person being still. Okay, so what about this downwards slope part of the graph? Well, for one, we can notice that, well, this slope here is a lot more steep than this slope, the first one. So first of all, you can imagine this part of the graph. The person has turned around and now he's walking in the opposite direction. So let's call this turnaround. Alright, so during this whole downwards slope of the path, the person is now walking in the opposite direction. Excuse me. So he's basically turned around, he's walked in the opposite direction. So just to kind of give a visual, you kind of imagine this is the guy here. He walks, and now here he's just standing. And then he turns around, now he's walking way back this way. So that's kind of what's happening for these first three parts of the graph. So let's call this part 1, let's call this part 2, I'll call this part 3. And then once down here at the flat part again, let's call that 4. That's a flat line. So you can imagine there he's just standing again, just standing still. And then here he's walking again. Okay, so that's not too bad. So for a position time graph, if there's some slope, that means there's some movement going on. If there's no slope or a straight line, then there's no movement going on. All right, so that's not bad. So now let me also talk about, I saw that. Let's draw it in again. So now I want to talk about the difference between the slopes of this graph. X. See? So I'll just say it first. The slope of this graph, slope, spelled that all wrong. The slope of this graph, if you kind of remember or have an idea of what the slope is whenever we deal with graphs. You guys can still hear me, right? I hope so. I think you can. Yeah. Cool. I'm gonna keep going. So the slope of this graph is, what do you think? Well, we know the slope is always going to be the rise over the run. All right, slope is always the rise over the run, or whatever the y coordinate is over the x coordinate. So it's right this way. It's going to be the rise over the run. And so for this position time graph, the slope is going to be, well, it's going to be the position, the x position divided by the time. All right, so the slope is the x, the position over the time. Okay, so that should look kind of familiar, right? That looks kind of like the velocity equation I just talked about, right? Where velocity is delta x over delta t. Oh, okay. So slope of a position time graph gives us the velocity. Okay, well, that makes sense, right? Well, it should make sense. So here then, I guess it's delta x and delta t for the velocity. So kind of imagine if you took, this point and this point, and we took the slope of it, right? Switch colors. So this would be like the final position here. That'd be x final. This would be like x initial. And so it'd be the final position, right? This final position minus this initial position. And then that would give us the velocity of that part of the graph here. Okay. So another thing I want to say about this slope is, notice the incline of this slope. Yeah, we can solve for, if there were numbers like, this here was 10 and this here is 20. We could solve for seconds. We could solve for the velocity of that slope. And so positive slope, positive velocity. Okay, makes sense. Now this one, a little bit different. It's slope, but it's sloped downwards. So that indicates a negative velocity, right? Well, when you have a negative velocity, I think somebody said this yesterday, that just indicates the direction, right? So this would be like negative direction. Close enough. So negative slope means you're going, or negative slope indicates a negative velocity, which then indicates you're going in the opposite direction. And then, of course, no slope here, slope of 0 means the velocity is 0. So you're standing still. Okay, so I think that's all I want to say about that. So now let's look at a velocity time graph. switch to my color. So the slope of this position time graph is velocity. So now let's look at a velocity time graph, and I'll draw it like this. Yeah, some bad lines, but kind of see where I'm trying to get a point. So velocity time graph. So the y-axis is going to be our velocity. The x-axis is going to be the time. So for this part of the class, whenever you're dealing with kinematics, it's always, and when you encounter these graphs, it's always important to look at what the axes of the graphs are. So it's important to notice that this is going to be a velocity versus time graph versus position versus time graph, or acceleration versus time graph. So now looking at this velocity time graph, let's look at each part here and try to say what's going on. So here, this first part, so that's 10. So for this first part here, this dotted blue line, it's a straight line. We could say the velocity is constant there, right? Because as time goes on, you're staying at a constant 10 meters per second. So you can imagine you're driving through a neighborhood and you're just kind of cruising at 10 meters per second. You're not accelerating, you're not slowing down, you're just kind of cruising at 10 meters per second. So here, that's going to be a constant velocity. All right, whereas for the position time graph, the flat line meant you were standing still. So for a velocity time graph, a flat line or a slope of 0 just represents a constant velocity. Okay, so it's constant velocity there, at a constant velocity here, and what do we think about this part here that's on the 0 that also has no slope? So this part is slightly different from the other two only because it's at the 0 here, right? So like this one right here, it's at 15. So as you go up on the graph, your velocity increases. But here, this is at 0. So at this point, while it's on the line, velocity equals 0. Okay. So now let's look at these slopes here. Switch colors. So for this part here, this positive slope, we could think of this as what you think. Well, basically we see it goes from 10 meters per second up here to 15 meters per second. And so he's basically speeding up, right? So for this positive slope, you're basically speeding up. So for the positive slope here, you're speeding up. So similarly, you can, you probably automatically guess then for this downward slope, you must be slowing down. All right. Now here's kind of a trick question. But do you think he's slowing down or speeding up here at this kind of slope that I'm bolding? You think it's speeding up or slowing down. And also notice that it's below the zero, so it's a negative velocity there. Um, do you think you're speeding up or slowing down there? Kind of while you think about that, while you take your guesses, while you say it's slowing down because it's a negative slope, while you kind of think about all that, I'm gonna, kind of drop hints to see if, see if you kind of get this, because it's not too obvious on what the answer is. So for one, we can say, well, it's below the zero. Okay, it's below the zero. So this is some negative velocity here. But okay, that's fine, right? Negative velocity just means we're going in the opposite direction. Cool. But it's also, a downward slope. So you might think, well, it's also slowing down. But it's not necessarily slowing down here. And let me kind of explain why. I'll just say it's actually speeding up here. So it's actually speeding up there. So let me be more specific with my words here. So for this part where I said it's sped up here, I'm actually going to draw it again. Clear. So at this part, and switch colors. So at this part here, where I initially said it sped up, well, what's really going on is this is a positive slope, and so slope for a velocity time graph, well, we know it's going to be the rise over the run, right? So it's going to be this velocity divided by, or over the time, right? So velocity over time. And so I haven't said this yet, but that's basically the acceleration. Acceleration. Okay. So the slope for a velocity time graph gives us acceleration, whereas the slope for a position time graph gives us velocity. Okay. And I say that specifically because here, this is basically a positive acceleration. And so we read that as speeding up. Here, it's a negative slope, right? So we read that as a negative acceleration. So it's slowing down. But down here at the bottom, below the zero, here it's negative slope, right? So we can also say that's a negative acceleration. But we also have to think, this is also below the zero here. So down here is negative, negative velocities. Negative velocity. Alright, so everywhere, below the blue, everywhere down there we have a negative velocity. So, again, a negative velocity just means your velocity is in the opposite direction. So the same thing goes for a negative acceleration. If you have a negative acceleration, it just means you're accelerating in the opposite direction. And so let me use some arrows to kind of represent that, or to kind of show why this is speeding up here. Right. So for an object to speed up, kind of right under here. For an object to speed up, the velocity and the acceleration have to be in the same direction. So we have to have a velocity, let's say, in this direction, and we also have to have an acceleration in that same direction. That's what causes something to quote unquote speed up. And so similarly, for something to slow down, so let's slow down. So for something to slow down, the velocity and acceleration have to be in opposite directions. So for something to slow down, we have velocity this way, and then acceleration has to be in this negative direction. So it's like negative A. Okay, so that makes sense. So kind of, oh, see if I got a laser pen. Yeah, so that I think makes sense, right? If the acceleration's in the opposite direction of the velocity, then that object is slowing down. If the velocity and acceleration are in the same direction, or they're both positive, then it's speeding up. And so what if, both the velocity and acceleration are both negative, which would kind of be what's happening down here, all right? So down here we have a negative acceleration, and we also have a negative velocity. So they're both going to the left. Let's my pen back. So over here you have negative velocity and a negative acceleration. So it's basically speeding up, but in the negative direction. Okay. So just want to point that out. And so let's see, what do we get from this? So overall, a position versus time graph gives us the slope. The slope of a position time graph gives us the velocity, whereas the slope of a velocity time graph gives us the acceleration. Okay. And lastly, I want to talk about is the area underneath this area here underneath a velocity time graph. Right. So this part of the graph, the constant velocity, this part that I have kind of filled in a bit, it's a constant velocity, and I'm talking specifically about what this area is under the graph. So this is just a square, and so the area of a square is base times height. So it'd be whatever this time is here times whatever the velocity on this side. So the area is going to be velocity times time. Well, velocity times time basically gives us the distance. Distance traveled. So all that just to say that the area underneath a velocity time graph gives us the distance. So that area there basically gives us the distance traveled at this constant velocity for that amount of time. All right. Okay, so now let's move on in. So that's all graph stuff, which tricky at times, but with just experience looking at it, I think it gets better and better. Oh, and I think the last thing I want to talk about was instantaneous velocity. real quick. Um, so let's say the velocity time graph looks like this now. Hmm. Yeah. Let's say the velocity time graph looks like that. Well, actually, no. I'm gonna just move on to the next part. Hmm, yeah. So let's actually just move on to acceleration then. Yeah, so far we've talked about displacement and velocity, so now, of course, we gotta talk about acceleration. So acceleration, first of all, we know it's a vector. So it has an x and a y component, right? And acceleration is given by the change in the velocity over the change in the time, right? Which we kind of saw that a moment ago from the velocity versus time graph, right? With the slope that gave us v over t, which is the acceleration. All right, so velocity is going to be a change in velocity in the x direction, all right, over the change in time. And so I have a quick example here, velocity. So a quick example here, where it says a car speeds up from 10 to 45 meters per second in 5 seconds. What is its acceleration? And so I think that's pretty straightforward. So car speeds up from 10 to 45 meters per second in 5 seconds. So we have the total time, and we have some change in velocity here. So we can immediately jump, and we can just say this is in the x direction. So the final velocity minus the initial, right? That's what that little triangle means. It's always final minus initial. So final velocity is 45 minus the initial, which is 10. And I'll also write the time out a similar way. Because I guess you've noticed there's a change in time on the bottom. So you can assume that this final time minus the initial time. But in almost all cases, the initial time is 0. So we kind of just, usually don't actually write out that whole thing on the bottom, but just to kind of show it. So 5 minus 0, 5, 45 minus 10, 35. So we can say, well, the velocity is going to be, the acceleration is going to be 7 meters per second squared, meters per second squared. Okay, so not bad. So far we've talked about displacement, velocity, speed. Let's talk about constant acceleration. Because again, we're talking about equations of motion and how objects move. In most cases, uh, either your either your acceleration is constant, which in most cases it will be, or it could be 0, or it could be non-constant. So your acceleration could be So you can have a constant acceleration, you can have an acceleration of 0, or you can have, what's the last one? A non-constant acceleration. For the most part, we'll just be kind of dealing with these two conditions, either an acceleration of 0 or a constant acceleration. If you have a non-constant acceleration, you can still, analyze with kinematics and so on and so on, but, it just takes a bit of calculus, integration and derivatives, which I'm not going to go through here, but, it's possible. But in most cases, we have constant acceleration and a 0 acceleration. So I kind of just want to show how that shows up here on these graphs. So acceleration versus time, velocity versus time. Let's just make this last one position versus time. So we have these three graphs here for a constant acceleration. So if the acceleration is constant, this first graph is just going to look like this. Right? Because constant acceleration just means, whatever the acceleration is, it stays the same. So if it's 5 meters per second squared, it's basically going to remain that throughout time. Okay, cool. So that's how an acceleration versus time graph would look. What about the velocity versus time? Well, if you have a constant acceleration, where acceleration basically means there's a change in velocity, the velocity versus time graph is just going to have it's just going to be steadily increasing. All right, so you can kind of think of constant acceleration as, this is you with your foot on the gas, speeding up, but yeah. So, and I guess you can also kind of look at it this way. If you look at this velocity versus time graph, well, let's look at this over here. Acceleration is positive. This acceleration is positive, right? And if we know the velocity versus time graph, the slope gives us the acceleration. Well, the slope must be positive. The slope so slope must be positive because the slope is the acceleration. Okay, cool. So for a constant acceleration, the velocity time graph gives us a straight line. And then lastly, for the position time graph, it's going to look something like this. It's going to be more of a parabola. Because as you speed up, you cover more and more ground. Okay, so I just kind of want to show those graphs so that I can then kind of get to the example part of the lesson where after I've kind of explained all of the groundwork, even though I glossed over it real quick, there's a lot of little nuances here and there that I skipped over, but you'll probably pick up in class. I just kind of want to give you the outline of kinematics. And so now we have these kinematic equations, which they'll introduce you to after saying most problems will be under the condition of constant acceleration. So these equations only apply only apply for a constant acceleration. Accelerator. I spelled that wrong. Okay. So these equations only apply for constant acceleration. And I guess that may sound limiting, but most, if not all, your problems will be a constant acceleration. Okay, so what do these equations say? Well, we got an equation for position here. Um, so it says the delta x here. I'm looking at this first one. Let's see, my laser. Looking at this first one. So delta x, or the change in position, is equal to v naught, where that subscript naught, or that subscript 0, just means initial. So this is the initial velocity here, times time plus 1/2 a for acceleration times the time squared. Okay. Then we have this other equation that says v, which that should be v final. This is v final. So v final is equal to v initial plus the acceleration times time. Okay. And last we have v squared, which that should also be final. So this should be v final. This is v initial. This is final. And again, all this is for the x direction. We say that too. All this is for the x direction. So this is v final in the x direction, v final in the x direction, x direction, acceleration in the x direction, acceleration in the x direction. Right. And there's also one more kinematic equation, but I'm not even going to mention it here. These are basically the three main ones. But there is a fourth one that you'll see in class, but it's rarely ever used, so I won't even bring it up. So these are our three main kinematic equations here for the x direction. And so similarly, we'd have these same equations for the y direction. So it would look the exact same way, except with the y. So, like for the y direction, it'd be, you guessed it, so y equals the initial velocity for the y direction times time plus 1/2 acceleration in the y direction times time squared, so on and so on. All right. The y. Okay, so you see it's basically the exact same equations except with the y instead of an x. So these are what we call our kinematic equations again, right? And we only use these equations when there's a constant. Okay, cool. So let me also show how these equations basically come directly from these graphs here in a way. I won't derive it completely, but I will say that these two equations, at least these first two, come from these graphs. So looking at this one here, look at this one. Let's look at that equation. Because this equation has this form here. Write it like this. Okay. I just switched the AT and the V naught just to kind of make a point here. So if you look at that equation has the form of a straight line. And so if you remember, that, so if you have a straight line, we can represent it with this equation here. So y equals mx plus b, right? Where, again, we know like y, b, whatever is on the y-axis. This b, this m here, I mean, is the slope. And this x is whatever is on the x-axis, and b over here is the y-intercept. Okay, so if you kind of look at it synonymously with that velocity equation above it, and we see, so like, I guess slope must be kind of associated with the acceleration. Okay, so if we go back here, we see slope is the acceleration. All right, so that lines up. The y-axis is going to be the velocity, and this y-intercept is also going to be velocity, right? So again, if we go back here, now we can imagine this here is the y-intercept, so this is like v0. Over here, that'd be like v final. And then lastly, t, which is for time, is going to be the x, so t should be on the x-axis, which again lines up here. You have t on the x-axis. Okay. So we see basically, just looking at this graph here, it gives us this kinematic equation. And you could have even gone, from this graph to this equation. And so next, if you look at this one, that's the last thing I'm gonna say about it. Look at all this. And so next, if you kind of look at this equation, and just kind of notice that the time here is squared, and this is the equation for position. And so if we go back and look at our position time graph here, and notice we makes this parabola, which on the other side makes this parabola. And whenever we have a parabola, it's it's x squared graphically, right? So kind of what I mean is, if we have this parabola, it's associated with this. Okay, so notice this x squared. So here it's time. It's time. So the time must be squared. So in this kinematic equation, we see that the time is squared, which is why we have this parabola form for this graph. Okay, so enough of that now. Let's get into some examples. So far, we talked about acceleration, displacement, velocity, acceleration. We talked about how that looks on graphs, how we interpret those graphs, what those graphs tell us, what the slope mean, what does the zero slope mean, all of that. And then eventually we get to these kinematic equations. Okay, cool. So now let's get into like a more kind of solid example, because all that's just kind of it's just the structure. So now let's get into a word problem. So here this problem says a car starts from rest and accelerates uniformly over a time of 5 seconds for a distance of 100 meters. Determine the acceleration of the car. Okay. So upon reading this problem, there's a few things we could take a note of as far as the words, right? So first, we see the car starts from rest. Right? So whenever you see something like that starting from rest, we can automatically say, well, the initial velocity is equal to 0. That's what that means. And then next we read this part that says accelerates uniformly. Accelerates uniformly. That means the acceleration is constant. So next we see that, we say, well, okay, a constant acceleration, boom, I can use these kinematic equations. And then so we see it says accelerates over a time of 5 seconds. So t equals 5. And the distance is 100. But I'm going to write it this way. I'm going to write delta x is equal to 100. Because, you know, we know delta x is final minus initial, right? But I'm just assuming here that it starts here at 0, the race car, because the race car starts at 0. And it accelerates all the way over here to 100. Okay. What else? What else? What else? Yeah, it's meters. Yeah. So far, so we started off by writing everything that they give us. All this is given in the problem, and we're trying to solve for the acceleration. So now here's kind of another problems that may be difficult for most people, because we have 3 equations here we can use. Really 4 if you were shown a 4th one, but I've kind of already knocked that one out for you. So then the next question is, well, which one of these equations do we even use? All right, this is final. So which one of these equations do we use? So at this point, we kind of just have to look at what the problem gives us. So we're given some initial velocity, we're given a time, and we're given displacement. And we're trying to find the acceleration. So you kind of just have to deduce, based off of the information given, which one of these would be the best one to use. So automatically, it's not going to be either one of these last two. It's not going to be one of these, right? Because we don't know what the final velocity is. So this one has a final velocity in it. We know nothing about the final velocity in this problem. So we can kind of, cross out these last two, and jump to this first one. And you say, okay, well, let's use that equation and see what happens. My pen out. So, of course, if you got a pencil and paper, I invite you to kind of work through this with me while I get this pen out. And if you've already kind of worked through it, just go ahead and type in whatever answer you got. Let's see if we match up. And again, we're going to use this equation, the first kinematic equation, or the displacement equation. All right. So this is the equation we're going to use. So kind of looking at the information given, um, we know we can go ahead and, since v naught is 0, we can go ahead and say, well, this whole part here, excuse me, that whole thing is 0. Okay, so that simplifies that equation a little bit. So now we're just left with this. And again, this is subscript. This is a subscript x. There's a pointer. There's a subscript x. It's not like x for position. It's just the x, the x component of the acceleration. Okay, so So now what? So we're trying to solve the acceleration, right? If you're working through this, trying to use this equation here, which came from the first kinematic equation, to solve for whatever that acceleration is in the x direction. And notice we know what delta x is, and we know what the time is. Okay, so we can solve for this then. Let me rewrite it then, so we using some algebra to solve for the acceleration. And how's my pen? Okay, so let me go ahead and do it. I'm sure some of you've already gotten an answer. So just rewriting that a little bit. The acceleration in the x direction is going to be equal to 2 times delta x divided by time squared. And if you're wondering where I got that from, I basically just went from here to here and solved for the acceleration. With some algebra, moved some things around. And now we can plug in everything they gave us. So we got 2, what, 2? Yeah, 2 times 100, which is 200 on the top. I'll just write it out now. So we got 200 on the top now. 5 squared on the bottom. So 5 squared is 25. 200 divided by 25, what's that, 8? Yeah. Okay, so we now know the acceleration is 8 meters per second squared. Okay, that wasn't so bad. Okay, so what if this question had a second part, which most of your problems probably will. Let's say there's a part B. I'm gonna add in a part B to this. So now we know the acceleration. So for part B, let me ask you, what then what's the final velocity at this point? Once it gets to that 100 meters, right there, what's that final velocity? All right. So what's the final velocity going to be? So go back to our kinematic equations. Let's go back up here. We look at these three, and we say, well, we've already used the first one, so we know it's going to be one of these two to solve for the final velocity. And if you're looking at these two equations and you're trying to find the final velocity with me, some of you probably said, well, we can use this one, and some of you might have said we can use this one. And then I would say, well, you're both right, right? Yeah, I would say you're both right. Because we can use either one of these equations to solve for the final velocity. And I'll just use them both, and they both should give us the same answer. So I'll use them both just to show that they both work. Let's see, so let's use that second one. So it looks like the final velocity is equal to the initial velocity plus the acceleration times time. Well, note the acceleration is 8, the time is 5 seconds, the initial velocity is 0, so that's going to be 40 meters per second. Okay, so let's use the other equation then. That says v final squared equals the initial squared plus 2 times the acceleration delta x. Okay, so initial velocity again is 0. Um, just kind of plugging everything in and then taking the square root at the end, right? So let me write that out. So take the square root of 2a delta x. So that gives us, let's see if it gives us the same thing. If we put that in our calculator, so 2 times 8 times 100. And boom, it gives us the same thing. Cool, so both of those equations work out. Okay, so again, no, not bad. It's just more a concrete example of how you're gonna basically be using your kinematic equations. So let's go to another example. So what's this one saying? So again, I invite you to work through this problem. I'll read it out loud. This is a race car accelerates uniformly. Again, notice these words that they use. Accelerates uniformly, letting you know that you can use your kinematic equations. Accelerates uniformly from 14 meters per second to 40 meters per second in 3 seconds. I guess that's fast. Determine the acceleration of the car and the distance traveled. So we want to find the acceleration and the distance traveled. Okay, so let's first start by trying to find the acceleration. So I guess the whole process, you can draw a picture, you know, if that helps. It just kind of, just because I like to draw pictures. Alright, got a picture look something like that, and you know, there's some delta x here. Don't know what that is, but you know the time is 3 seconds. Okay, well there's our picture. You know, some people are more visual. Sometimes having a picture just helps people kind of, you know, just get it down on paper. It just kind of helps them in their mind. So we got all that. So once you have a picture, you would then, you know, write out what they give us. So they give us an initial velocity, they give us a final velocity, and they give us a time. Okay, so all that's the given stuff. Meters per second. And that's supposed to be a 4, not a 9. Okay, so we got all of our given stuff, and we want to find the acceleration. So we go back to our kinematic equation, and we look at them, and we say, okay, we're given a final velocity, an initial velocity, and the time. Which one of these can I use to solve for the acceleration? Well, we can automatically cross out the first one, right? The displacement kinematic equation. We can cross that one out because we don't know, we don't even know what the displacement is, and we don't even know what the acceleration is. So we don't even have enough information to kind of to even use this equation. We say, okay, well, let's look at the second one. Well, the second one gives us the final velocity. Okay, we know that. Initial velocity. Okay, we know that. And acceleration, don't know that. We're trying to solve for it, but we do know the time. Okay, so we know, you know, 3 out of the 4 quantities here. So we can use that one. So I'll get my pen out. So again, you know, if you're working through this, go ahead and type whatever answers you got in on the chat. You know, just so we can kind of see where you're at. You know, we're gonna use this equation, right? The second one, the final. Plus AT, right? So we're trying to solve for that acceleration. Use a different color. It's, green looks crazy. Right, try to solve that acceleration. So another thing that's you probably do is you probably, you know, you probably look at this equation, you probably, well, okay, let's use that one. And you probably just go jump in and plug in your numbers, something like this, right? I imagine this is just naturally what most people do. They just say, okay, you can plug the numbers in, and that's a 3. But then they kind of go about it from here and say, okay, well, it's 40 minus 14, and gotta move that over. Let's see, what a 3a. And then you probably kind of go about it this way. So 40 minus 14 is what, 20, 26? No, 20, yeah, 26. Yeah, okay. And then you divide the 3 over, so you say a is equal to 26 over 3. Okay, and then you know put that in your calculator and get some decimal answer. So that process is fine, that's cool, there's nothing wrong with it. But I would invite you to instead, you know, while you're in this physics class, to always try to solve for your answers symbolically before you put in your numbers. So what I mean by that is, instead of putting your numbers in, let's go ahead and solve for the acceleration first. So the acceleration is going to be final velocity, right, minus the initial velocity divided by time. Right? Just get some algebra, move some stuff around. Let's get that. And then plug in, you know, all this stuff over here. See, it's the same thing, but right there, right there, right there. So yeah, same thing, 26 over 3. Okay, so now we got the acceleration, cool. Just being over thorough, right? You know, you probably already determined the acceleration, then went about solved distance. So now we got our acceleration here. So the distance, so how are we going to solve for that? We can use, it looks like we can use either the first equation or the last equation. And so you use either the first one or the last one. Because now we know the acceleration, so we can use either one of those. I'm just going to go ahead and use the first one. Let's determine this distance. Let's use that first equation, delta x equals v naught t plus 1/2 a t squared. Looks like it's going to be a little messy. Initial velocity was 14 times 3 seconds plus 1/2 acceleration 26 over 3 squared. Okay, so do all that, plug all that information in, and then we can solve for what our delta x is. Yeah, so I'll leave that to you to kind of just put that in your calculator and work that out. I'm going to go ahead and move on to the next slide. So we've got a few more examples. I'll do this example, and I'm getting to projectile motion. And then projectile motion is kind of where I'm going to end it for today. So let's do these two quickly here then. So now I've got a car traveling 42 meters per second, skids to a stop in 3 seconds. Determining the skidding distance of the car, assume uniform acceleration. Okay, uniform acceleration, so that means we can use our kinematic equations. So let's kind of see what this problem is telling us. We've got this car here. Um, you know, it's skidding on the ground, coming to a stop, right? So I don't know what kind of car that is. But we know this initial velocity, they give us that is 42. Oh, it comes to a stop. So to the final velocity is 0, 42. And we're trying to find this distance here. And what else? We know the time it takes is 3 seconds. Okay. So again, you probably go look at your kinematic equation, look at what's given, um, and see which one of those equations best fit this problem. So if you're looking at those equations, you probably already guessed it, that it's probably best to use this one, that second kinematic equation. Okay. Um, Ooh, actually, wait a minute. We're trying to solve for the skidding distance, not the acceleration. Hmm. So it seems this might be like a two-step problem because we need to know what the acceleration is before we can even solve for that distance, right? So let's use the second kinematic equation to solve for the acceleration first, and then we can solve for what that distance is. So we write in that v final minus v initial divided by the time, right? Just rewrote that equation. So then it's going to be basically negative of what's 43 divided by 2, I think 14. So it's basically going to be negative 14. Okay. Okay, that makes sense because this car here is slowing down and coming to a stop, so the acceleration must be negative, or the acceleration must be in the opposite direction of the velocity. Might be a better way to say it. So what I mean by that, color here, what I mean by that is this car has a velocity this way, and since it's slowing down, the acceleration must be this way. Okay, so velocity and acceleration in opposite directions, right? Indicates that it's slowing down. Makes sense. And so it makes sense that we get a negative acceleration. All right. So now, let's now use that last kinematic equation, this one, to solve for delta x. So we write in it, we see that delta x is basically equal to v final squared minus v initial squared divided by 2a. Right. So now at this point, I'm not gonna write out the answer, but you can put in numbers. So 42, or 0 actually, and 0 minus 42 squared. All right, all that divided by 2 comma negative 14. All right, so with that we can find our displacement, which is going to be, looks like 63. Okay, cool. All right, so this last example I'm gonna do before I get into projectile motion. Um, so this problem is what we call a free fall problem. This is free fall. So a free fall problem is basically another form of a constant acceleration. right? So free fall, another form of constant acceleration. So this problem basically says that we have a kangaroo is capable of jumping to a height of 3 meters. Um, I'm not sure if that's true or not. That seems really high, but it is a kangaroo. A kangaroo is capable of jumping to a height of 3 meters. Determine the takeoff speed of the kangaroo. So kind of noticing this problem, it doesn't necessarily say anything about, the acceleration being uniform or anything, but I don't know how it looks. That's my kangaroo. So this kangaroo, it hops up and it goes up 3 meters. So yeah, this problem doesn't necessarily say anything about, the acceleration being constant, but what they want you to realize is, um, in all the problems up until this point, we were looking at the x direction, right? So we're dealing with a lot of cars. Like this car is in the x direction, this car is in the x direction, and another car actually in the x direction. So all those have been in the x direction. This problem, the kangaroo is going up and down, so he's jumping up in the y direction. So what's really different about the x and the y direction is in the y direction, there is automatically constant acceleration because of gravity. So yesterday, we talked about this gravitational constant g, and we said it was 9.8 meters per second squared. So that's an acceleration. If you look at these units, that's an acceleration. So that g is basically the acceleration for the y direction. It's magnitude at least. So that's the acceleration in the y direction. So any object that's falling down or going up is going to experience this acceleration due to gravity. Okay. Okay, cool. So yeah, so this kangaroo is capable of jumping to a height of 3 meters. So when you jump to your maximum height, you can kind of imagine if you throw a ball up, you're standing here and you throw a ball upwards. The ball goes up and goes up depending on how hard you throw it. Let's say it goes right here. That's at its max. Once it gets to that max, it's going to pause for a brief second, right? And then it's going to start to fall back down. So one thing we can say about, once you reach this max height, we can say the final velocity is equal to 0. So like if down here was the initial velocity that you threw it up at the top is going to be, well, at the top your velocity is going to be 0 because the ball pauses for a second. Right? I think that makes sense. So you kind of apply that idea to the kangaroo here. So we can say solve for his initial velocity. That's a question mark. His final velocity is 0. And delta y now is 3 meters per second, or meters, right? That's how high he jumps. And lastly, the acceleration in the y direction is equal to negative 9.8. And I'm putting the negative in here now because uh, it's pointing downwards, right? Or here I wrote it as the magnitude. Okay, so this is kind of what we are given in our problem, and we're trying to solve for the initial. Okay. So it looks like maybe the best equation to use would be the first kinematic equation. Yeah, let's use the first kinematic equation. Yeah. Which, let me write it this way. All right, delta y the initial y direction. Oh wait, no, we can't use that one. Scratch that. Let's use the last one. Plus 2a y delta y. There we go. Cool. So now we have this equation. We're trying to solve for the initial velocity here. So let me rewrite it this way. This is 0. So the initial is, so let's see. It's going to be the square root of, we subtract that over, it's going to be minus 2a y delta y. All right, where that minus came from, because I had to move that to the left-hand side, right? It came from the algebra. So then when we plug in our numbers, and also notice that this negative here is going to cancel out with that negative. So the initial velocity of this kangaroo must be, oh, I don't know why I wrote it like that. So negatives cancel out, so it's going to be positive. So 2 times 9.8 times what? Times 3? So let's plug that into our calculator and see what we get. So it's the square root of 2 times 9.8 times 3. Get 7.6. Yeah, 7 point. Actually, just round it up 7.7. All right. So now we've gone through that. Okay, so that was free fall. So that was supposed to be my kind of segue, I guess, into projectile motion. Where basically projectile motion is kind of a combination of this free fall problem mixed in with, this car is moving in the x direction. So let me kind of show how. So since this is the last part I'm going over, I just want to get the concept down of projectile motion. So you could think of projectile motion as it's a 2D motion. So far we've been dealing with motion in one dimension. And so you can already kind of imagine, I imagine everybody's thrown an object before or seen an object thrown before. Whether it's your phone, whether it's a ball of some sort, a rock, I don't know. Anything you throw is gonna basically go in some type of projectile motion. So if we have, some object here that we throw at this angle, so it has some initial velocity, we know it's gonna take some path like this. All right, and this is the y direction, this is the x direction. All right, so this is visually kind of what projectile motion is. So kinematics basically explains why an object even goes in this arc-like path in the first place. Yeah. So as this object basically goes through this arc-like path, we know it's being pulled down by gravity, right? The acceleration that's happening here is acceleration in the x direction. So acceleration in the y direction is equal to negative 9.8. So the only acceleration that's happening here is this acceleration in the y direction. And let's see, yeah. So, what does that necessarily mean? So it kind of means as this object here goes through its path, it goes up and up and up until it reaches this maximum height here, and then it starts to fall downwards. So let me also draw the components then of this velocity vector, because now we're dealing with motion in 2 dimensions. So there's some x component, right? There's v naught x, initial velocity in the x direction, and there's also v naught y, initial velocity in the y direction, which we know both of those are, we can rewrite those in terms of sines and cosines. So we can automatically say, well, v naught x is going to be the magnitude of the initial velocity times cosine theta v naught y. It's going to be the magnitude times sine theta. Okay. So let me draw both of those. Use a different color. So yeah, this and this here. Oh, let me pick a few points along this path here. So I'm gonna choose that point, choose that point, I'm gonna choose this point, this point, this point, this point, this point. Okay, so and at each one of those points, I'm going to write out how the velocity components look, starting with the x component. So in the x direction, so we know there's acceleration in the y direction, but in the x direction, in this direction here, the acceleration in the x direction is actually 0. There is no acceleration in the x direction. There's only this acceleration in the y direction. So if acceleration in the x direction is 0, that means that there is no change in velocity in the x direction. Okay. So this means there's no change in velocity. No change in velocity in the x direction. No. I'm just trying for change, I guess. No change in velocity. Yeah. Excuse my handwriting. So so let's get each one of those points then. So here at this point is going to be some velocity in the x direction. Okay, so here at this point there's going to be some velocity in the x direction. Again, that velocity is not changing, right? It's basically staying the same. Okay, so all those represent the x component of the velocity as it goes through this path. So let me now draw what the y component is going to look like. So just yellow. All right. So there is an acceleration in the y direction. So the acceleration, since there is an acceleration in the y direction, the velocity is going to change for the y direction. And that's basically what's causing this to be an arc-like path. So for this next point, the velocity is still upwards, but it's a little bit less now. Here it's upwards, but a little bit less now. And here it's up, but even less still. And then here at this point, at the top, the velocity in y direction is equal to 0. Alright? Because kind of like in the kangaroo scenario, once the kangaroo got to the top of its path here, the velocity in the y is equal to 0. Alright, so it's whenever an object's at the top of its path, the y component of its velocity will be 0. And so now, okay, the ball, rock, whatever it is, starts to fall downwards now. So here, got a little tiny velocity vector pointed downwards. Here it's a little bit longer. Here, a little bit longer. And that's because it's speeding up as it falls down because of gravity. And then here, it's still pointing downwards, still moving even faster. Okay. So this is the whole projectile motion picture that I wanted to get down. I think a lot is being said in this picture that you only kind of pick up with time and as you go through more examples. So again, notice how in the x direction it's light blue color. In the x direction there's no acceleration. So the velocity vector for the x direction is constant. So it's just going at a constant velocity in the x direction. But in the y direction, notice how it has most of its y velocity initially. It decreases because as it goes up, it's slowing down as far as the y direction is concerned. And then it reaches the top and it starts to fall, and it starts to fall faster and faster. All right, cool. So let's see. Let's do this last example and I'll wrap it up. It's 10:58. So this example here says a batter hits a baseball so that it leaves a bat at a speed of 35 meters per second at an angle of 60 degrees. Find the position and the velocity of the ball at 2 seconds. Find the time when a ball reaches its highest point H and find the range of the ball. Alright, so there's a lot of stuff being asked here. So again, we're still doing kinematics, so we're still going to use those kinematic equations. So let's draw the picture first. We've got this ball hit at this angle of 60 degrees. And it tells us that the initial is 35. Right. So this ball is gonna go through some type of motion like that. And so the range is this here on the bottom. That's the range. This here is H, which is its maximum height. Okay, so now let me write out the kinematic equations for the x and the y direction. So if you look at the x direction, x direction. So one thing about the x direction we know is the acceleration is equal to 0. There's no acceleration in the x direction, so when we write out our kinematic equations, they look like this. equals v not in the x direction times time, let's see, plus 1/2 a in the x direction times time squared. Well, all this is 0, alright, because acceleration is 0 for the x direction. What did the other equation say? Well, final for the x direction is the initial x direction plus a t. Well, acceleration is 0. So this just says the initial acceleration in the x direction is equal to the final velocity. The initial velocity in the x direction is the same as the final velocity in the x direction, right? Which makes sense with this picture, right? Because the velocity staying the same throughout its whole path. Okay. And then the last kinematic equation is basically going to say the same thing. I'll just slightly write it out. Right. Both of those are equal because the rest of this is 0. Okay. So not much going on here for the x direction. So all we really have is this equation here, kind of, for the x direction. For the y direction, no. I know we're getting close to that time, but I just really want to write this out. So for the y direction, so the acceleration in the y direction, because it's due to gravity, it's negative 9.8. So let me write it this way. Let's just say it's negative g for now. So that way, when I write it out in these kinematic equations, I can write it a certain way. So v, or delta y equals v naught y times time minus 1/2 g t squared. Okay, so that minus came from the fact that the g is negative. Okay, so what's the next one? V final equals v initial minus gt. V final squared equals v initial squared minus 2 minus g delta y. Okay, so notice kind of the difference here between so we got these equations for the y direction, got these equations for the x direction. Okay, and so now quickly kind of solving for this first part, it says find the position and the velocity of the ball at seconds. Alright, so let's switch colors real quick. So we got about 5 more minutes. So I'm just gonna kind of end it working through this. So let's first solve for these components here, this v naught x and this v naught y. Okay, so we can do that real quickly here. So v naught x, all right, is the x component of this velocity. So it's going to be v naught times cosine 60. Okay, so we know those numbers. We know 35 cosine 60. I think that's about 35 divided by 2. What's that, 17.5? 17.5. Okay, so that's our x component of the velocity. Let's do v naught y then similarly. Plugging in those numbers, we get, let's see, It's about 30.3. Okay, so now we've got our initial velocity in the x direction and our initial velocity in the y direction. Okay, so now we can find the position at 2 seconds. We can solve for this position now at 2 seconds. So we have to solve it separately for the x and the y direction. So if we look at the x here, well, the x position is going to be, what's that, 17.5 times 2 seconds. Okay, so that's just, what, 35, I think, 36. So it's 35 meters in the x direction. And so how far is it in, or how high up is it in the y direction? So delta y, we have to use this equation. So delta y is going to be equal to, that's 30.3 times 2 minus 1/2 times 9.8 times 2 squared. And notice the minus from this 1.9 is up here in the front now. It's already kind of included for us because of the way I wrote it. And so I'm not going to put that in my calculator, but we can see we can now solve for the y position. So it equals so and so. Okay. So since I am running out of time, I will just leave it for you to solve for the rest of this problem, just to kind of give you a few hints if you're really going to work on it. To find that time. So the next part, so we saw, oh well, they want the velocity too of the ball at t seconds. So we found the position, solved for that. We can also solve for the velocity at 2 seconds by using the second kinematic equation for both, right? So we can use, well, we know v final in the x direction is equal to v initial in the x direction. So that component of the velocity is just that. And so we can also solve for the final velocity in the y direction. It's going to be v naught 1 minus gt. So you can solve for that too. We know this. And we just plug in those numbers. Okay, so then you'll be able to solve for the velocity of v final x, comma v final y. Alright, so quick hint on how you solve for the velocity, how you would solve for the time when the ball reaches its highest point h. Well, we'd have to set the condition that at this point up here, that the final in the y direction is equal to 0. Okay. Then once we do that, we can jump to this equation again, actually. Yeah, using that equation again, we can set v final equal to 0. We know what the initial velocity is, and then we'll be able to solve for that time there. Let's kind of jump into it. Yeah. Yeah, okay, and the negatives are cancel out, right? Okay, so that'll solve for the time, and then I guess I'll leave it up to you to solve for what's yeah, not just leave the rest up to you. So yeah, that's it for the physics camp. Um, it's been fun. I hope that these kind of brief introductions kind of give you a heads up for the class, so that and when you see these things in class, they won't be so new to you, so unfamiliar, and so intimidating. Uh, I tried to kind of work out some key concepts for you to see with projectile motion and these graphs here, which you'll probably see a lot of. What else? What else? Yeah, that's it. So, leave your feedback. It's been fun. I hope all this helps. Discard. Yeah, thanks everybody. Thanks everybody for coming. Thanks for attending. Thanks